Hello, everyone, and welcome back. Today and tomorrow, I would like us to take some time to explore how the definite integral is used to study objects that are in motion. And today, we will be focusing on an object which is moving along a linear track, an object that is moving in one-dimensional space. And tomorrow we will talk about what these ideas look like if you have an object that is moving in two-dimensional space, not necessarily along a straight line, but potentially along a curved path or track. So first of all, I want to either review or introduce to you two pieces of terminology that are used to describe a moving object. And the two pieces of terminology for today are displacement and distance traveled. If you have an object that is moving along a straight line path, then we say that displacement is the difference between the object's position at the initial time and the object's position at the final time, in specifically the order of final minus initial. That is the order of this difference. Meanwhile, if you want to talk about the object's distance traveled, then distance traveled would be the total distance that is traveled by this object between the initial time of movement and the final time of movement. Now let's talk about what makes these two terms distinct from one another. What's the difference between displacement and distance traveled? To show you the difference between displacement and distance traveled, consider the following scenario. You've got a person walking along a straight line path. Let's just note it with this horizontal line here. And they start out at an initial position right here. Let us suppose that this individual, starting at this initial position, walks forward, let's say 2 meters, then turns around and walks backward 1 meter. Then this individual turns around again. Maybe they went back to pick up the keys that they dropped on the sidewalk, and they keep walking forward again. And they walked forward now, let's say 3 meters. And so in the end, they wound up in a position that is +2, then backtracked 1, and then +3. They wound up at a position that is 4 units away from where they started. So in this terminology, for this person who walked back forward 2 meters, back 1 meter, and then forward 3 meters again, this person's displacement would be 4 units. And that 4 units would just be found by summing up all of these movements forward by 2, backward by 1, and forward by 3 to get a total of 4. And this would be the difference between the object's final position and its initial position in the order of final minus initial. Now, by contrast, if somebody had asked you to calculate the total distance traveled by this object during these two periods of time, then the total distance traveled be 2 meters were traveled in this moment, 1 meter was traveled in this moment, and 3 meters were traveled in this moment. In total, 2, 1, and 3, all of those movements would be counted as positive because we're just looking at how far this guy walked, not the direction in which this guy walked. So the total distance traveled by this person, including this backtrack here in the middle, would be 6 units. From 2 units forward, 2 units backward, and 3 units forward, but all of those distances would be treated as positive because total distance traveled doesn't care whether you're going forward or backward. And to capture that, we could think about this as applying an absolute value to eliminate the negative sign on each of those movements. Bear this in mind, this absolute value is going to be important, and it's going to come back later. So in other words, in one-dimensional space, distance traveled treats all this person's movement as if it were in the forward direction. Or put another way, it treats all the movement as if it were positive. And mathematically, you could think about this as being sort of connected to an absolute value, because absolute value also sort of treats all numbers as being positive. Now, to further expand on this idea, let's begin with a really simple example of an object that's moving at a constant velocity. And then we will use the chop, multiply, and add sort of principle of calculus 2 to extend this idea to more complicated situations. So we have an object which is moving at a constant velocity of negative 20 meters per second. Constant velocity of negative 20. And they're moving for a time period of 8 seconds. I'm going to call it delta t for our period of time. Our interval of time here would be 8. So if we wanted to know the object's displacement, how could we calculate the object's displacement from this velocity and from this time interval? Well, what this is saying, if I were going to sketch out this situation, is that this object started at some initial position and then moved backward because we have a negative velocity, moved backward at a speed of 20 meters per second, and they moved backward at that speed for 8 seconds. So all in total, they moved backward over, looks like 8 meters. 120 times 8, which is 160 meters. And they ended up in a final position, which is 160 meters behind where they started. So if I were going to do the displacement, I would be doing final minus initial positions. And so the final position minus the initial position would be negative 160 meters. Negative 160 meters because the final position is behind the initial position. In other words, the displacement is exactly equal to the velocity with its negative sign on the 20 to indicate the object is moving backward times the time interval. Velocity times time interval is exactly equal to displacement if you have constant velocity. Because if the object is moving backward, then the final position is behind the initial position. And likewise, if the object is moving forward, then the final position is in front of the initial position. So all of the signs match up. If you have negative velocity, you'll get a negative displacement. And if you have a positive velocity, you'll get a positive displacement. Now, by contrast, let's, for this same situation, ask how far did the object travel during that time? Well, if we're asking how far the object traveled during this time, distance traveled doesn't care that you were moving backward during this period of time. Distance traveled treats all of your movement as if it were positive in the forward direction. So in this case, if I want the distance traveled, all I would have to do is strip the minus sign off of the velocity and take this positive value of positive 160 meters, and that would be the distance traveled by this object. In other words, the distance traveled could be found by taking the absolute value of your velocity, stripping that minus sign off, and multiplying that by the amount of time that has passed. Okay, bear this in mind as we go to the more complicated example. If we are if we are dealing with a velocity that is constant, or which we are treating as constant, then displacement is just velocity times time interval, and distance traveled is the absolute value of velocity times the time interval. Bearing that in mind, let's go to our second exercise here. We have an object which is moving along a linear track, but the velocity of that object is varying over time. It's not constant. Now we have gone into our table, and in this table we have recorded the velocity of the object every 5 seconds. So the initial velocity of the object was 0. At 5 seconds, it was moving forward at a speed of 10 meters per second, and so on. At a time of 20 seconds, it was moving backward at a speed of 4 meters per second, and so on. Now, someone says, based on this information, let's estimate the total displacement of the object between time 0 and time 60. We're going to use this idea that is surfaced in this class very often. What I'm going to do is set up what is essentially a Riemann sum. And I'm going to assume that the velocity is constant in between the periods of time that are recorded in this table. And with that assumption, I am going to add up over all of our intervals of time the velocity at some random time chosen from the ith time interval. And then we're going to multiply that velocity by the time interval. Because as we saw in this previous sort of toy exercise, velocity times time interval is what gives you the displacement on that time interval if your velocity is constant. And so we're doing that here for each time interval, and then we're just adding it all together to get the total displacement. This is what it would be symbolically. And if I went ahead and used my table to write down what this would become as a number, let me go ahead and do that real quick. Okay, so here I have written down what this sum would become if I used the left-hand velocity recorded on each time interval. And so I have, for example, 0, and then 10, and then 20, and then 5, and so on. And I've multiplied each of those velocities by the time interval between my data points, which here is 5 seconds. So based on that, according to the calculator, the displacement in this situation is positive 315 meters. So we would estimate based on this data that the object's final position was 315 meters in front of its initial position, because we have this positive displacement here. Okay, now let us make a note. We have written down what this would look like as a Riemann sum. We would written down what this would look like in a situation like this where we have relatively few data points that are pretty far apart. While we are here, let's do the usual thing of making a note on the side of what this sum would become if we had enough data to treat it like an integral. As usual, if we have a lot of data, this sigma stretches out into an integral symbol from whatever is your initial time to your final time. As usual, if you have a lot of data, this v of ti star transforms into simply v of t, with no I and no star anymore. And additionally, if you have a lot of data and the space between your data is small, this delta t transforms into a dt. So I'm going to write this down. If you had a ton of data and you wanted to try and find the total displacement of the object between two times, then you could do that by integrating the velocity function. Now I want to pause here and I want to make sure that you understand why I go through this exercise with you, why I start by writing it down as a sum and then thinking about what it would become as an integral. Studies have shown that students who learn Calculus 2 often really have a hard time knowing how to apply Calculus 2 ideas in real-world applications. Studies have found that Calculus 2 students usually are very well trained at how to calculate integrals, but have a very, very difficult time in the real world knowing what integral to set up to correspond to any given situation. And that's what I'm trying to work through with you here. If you have a real world scenario like this one, if you have a real world problem that you're trying to solve, like displacement or distance traveled, a real world quantity that you're trying to calculate, I'm going through this exercise with you so that you understand the process by which we know what kind of integral we should even set up to try and answer that question. We usually start with a toy example where everything is really, really simple, and you can find the answer easily just using algebra. Then you say, okay, suppose it's not that simple. Suppose maybe it's not constant. Suppose it's varying, and I had a table of data. What would it look like if I applied this chop, multiply, and add process to the data in that table? What would that look like? What would that look like as a Riemann sum? And then transform that Riemann sum into an integral, allowing the space between your data to get really small so that your sigma becomes an integral sign, your delta t becomes a dt, and your ti stars become t's. This is what I'm trying to demonstrate to you, this idea. Let's get more practice with this idea, and let's try and figure out what kind of integral would be needed to calculate not displacement for this object, but distance traveled. Now we observed that distance traveled in this sort of toy scenario up here. If you have a constant velocity, distance traveled can be found by taking the product of your absolute value of velocity with your time interval. In other words, taking the product of the speed of your object with the interval, delta t. So let's use that idea down here as well. If I wanted to find the total distance traveled by the object between these two times, then I could do almost the same thing that we did in part A for the displacement. Except in this sum, I'm not going to be doing velocity times delta t. I'm going to be doing speed times delta t, where I take each of these velocities and apply the absolute value to make them positive and treat them as positive. Now, once again, we can ask ourselves, what does this become if we had a lot of data and this could be thought of as an integral? Well, this could be the integral from the initial time to the final time of the absolute value of your velocity function times not delta t, but if you have a lot of data, dt. And it's this integral of speed, this integral of the absolute value of velocity that could be used to calculate distance traveled. Now, in our particular example, if I once again decided to use a left Riemann sum to calculate total distance traveled, all I would have to do is basically copy paste what I had for the distance traveled, and every time the velocity is negative, just change it to positive and treat all of them as positive. And if I do that, then the distance traveled according to the calculator is 545 meters, approximately, according to this data set. So the object backtracked for a little while, between time 20 and 30 at least. So of course the distance traveled in total is going to be larger than the displacement, because the displacement is allowing the back and forth motion to cancel itself out, whereas the distance traveled is just adding everything up entirely, treating it all as positive. Okay, now that we've gone through these exercises, let's go ahead and write down the formulas for distance and displacement, as can be calculated using integrals. If you have an object moving in one-dimensional space, in other words, along a track shaped like a straight line, either backward or forward, and you know the velocity of the object at any given time, the velocity function v of t, then if your time period of movement is between an initial time called A and a final time called B, then the displacement can be found simply by integrating the velocity function between these two times, and as well distance traveled can be found by integrating the speed of the object between those two times, the absolute value of v of t. These are the two formulas, the two integral formulas that can be used to calculate displacement and distance traveled of an object from its velocity. Let's get some practice using these formulas in one additional exercise. In this exercise, we're given the velocity function not as a table of values this time, but as an actual formula. V of t is equal to 50 minus 10 times t. And this describes the velocity of an object at any time t. So if this object is moving between time 0 and time 7, let's go ahead and calculate the displacement. Well, now that we have figured out what integral formula can be used to calculate the displacement in a situation like this one, all we have to do is integrate from 0 to 7 our velocity function, dt. And this velocity function is really nice because each of the terms in this velocity function is just a power function or a constant. So the antiderivative can be found very, very easily just using power rule. And because I have an easy antiderivative, I would definitely be calculating the value of this integral using fundamental theorem. So the notation that I like to use is this. Here is our antiderivative of 50 minus 10t. It becomes 50t minus 5 over 2t squared. And then on the side, I've put this bar, and I've put t equals 7 on the top and t equals 0 on the bottom to remind myself that the next step in the fundamental theorem process is to plug in the upper limit of 7 to this function, plug in the lower limit of 0 to this function, and then subtract the two results. Now, if I simplify this result with the help of our calculator over here on the side, we find that the displacement of this object with this velocity function is equal to 280 units, probably meters. So this object has ended up in front of its initial position. Fantastic. So we were able to find the displacement of this object just by integrating the velocity function using fundamental theorem. Now someone says, same scenario, but this time I want the distance traveled. And if we want the distance traveled, we have now figured out that what we need to do is integrate the absolute value of the object's velocity. What we need to do is integrate the object's speed. So I need to integrate absolute value of 50 minus 10t dt. So how am I going to calculate this definite integral? Well, the game has changed compared to part A because now I have absolute values on this function. I no longer have an integral rule that I can use to easily find an antiderivative of 50 minus 10t with the absolute values on it. So as we talked about a couple of days back, if I'm in a situation where I cannot use odd symmetry, And if I'm in a situation where I cannot easily see an antiderivative, my next move is to go to Desmos and to look at the graph of this function to see if the graph of the function has a geometry that I can use. Okay, so here I have the absolute value of 50 minus 10x graphed below, and I can see that the region under this graph is geometric. It consists of two triangles. Triangle number one here has a height of 50 units and a width, a base of 5 units. So that would contribute to the total net area, 1/2 50 times 5. In addition to that net area on the left side, we have a little baby triangle over here on the right side as well. Looks like this triangle has a height of 20 units and has a base which is 2 units wide, 20 and 2. So putting both of those values together, this looks like 125, this looks like 20, so all in total, we're getting 145 meters. Now, already my alarm bells are going off. I feel like I made a mistake in here somewhere because it doesn't generally make sense. I don't think it ever makes sense for the distance traveled to end up less than the displacement. So having noticed that something seems to be wrong, let me go into my work and let me try and figure out what mistake I made that led to this particular outcome. Because this doesn't make sense. I know for sure a mistake was made somewhere. Aha, I think I spotted it. My mistake was in what I typed into the calculator to try and find the simplified version of the displacement. So let me go ahead and fix that typo. And now I have a typo here in the antiderivative of this function. The typo that I made is that I sort of divided 10 by 2 in my mind and turned it into a 5, but I also wrote the division by 2 here as well. So I divided by 2 twice, and that gave me an incorrect value there. 50 times 7 minus 10 over 2, 7 squared. Now we are getting a displacement of 105 meters. 105 meters. And now I'm much more comfortable with this result. Because now the total distance traveled, treating all of our movement as positive, is larger than the displacement, which treats some movement as negative, and there's a little bit of cancellation that occurs in the sum. So now this actually makes sense, and I want to include this mistake in the video once again because I think it'll be useful for you to see the reasoning by which I knew I had made a mistake and by which I was able to catch it. Okay, this concludes today's video talking about distance traveled and displacement for an object moving in a line.